So, okay. First of all, I'd like to thank the organizers for putting together this this workshop and this very exciting program. And today, I'm truly excited to tell you about some recent work by our group focused on the control of strongly correlated states in quantum materials with light. In particular, we focus on long-term project on achieving quantum control of Hubbard excitons. The first steps in this work are reported in a manuscript which is currently under review. The referees got back to me today. Without further ado, let me get started. So I like the first two talks, or let's say in a different spirit with respect to the first two talks of the session. Today I want to tell you about how we can actually achieve control of quantum materials properties with light. So there has been an explosion of this field in the past couple of decades. And in general, the basic idea is that we use...
So we're hoping longer than anticipated. Okay.
Okay. So basically, we in this area, we aim to use intense laser light to drive materials out of equilibrium and achieve different states that can have, as an example, different functionalities, or even tune the ground state in novel ways. So this field has undergone quite some evolution over quite a long history. And it started with some experiments that involved excitations with high energy photons, mainly focused on structural transitions that induce some melting and thermal phenomena, and generally led to effects that were described in terms of effective temperatures and with very strong decoherence effects. The availability of laser light at terahertz and mid-IR frequencies has ushered in a new era involving more precise and selective coherent control problems, in which we can use light with low energy, with low photon energy, in order to control collective modes and order parameters in materials. As an example, we could displace structures and thus increase new responses and new functionalities in a way that was both selective and reversible. But now the frontier, and what I'm really and what my group is really after, is to go towards something that is more like quantum control, meaning that besides achieving some selective and reversible control of microscopic observables, a big question for the field is whether we can actually tailor Hamiltonians on demand, whether we can deterministically and reversibly alter quantum states in a more accurate fashion. This is achieved in a variety of ways, through optical dressing in free space, more recently through work with hybridization in cavities that has been pioneered by many groups, among them Lucan's group, here at Rice. And the basic idea of all of this is to really use light to achieve control of quantum degrees of freedom towards a rational design of non-equilibrium states of matter. So one way to do this is through the so-called Floquet engineering, Floquet engineering in the context of quantum materials means that we use strong mid-infrared light or strong electromagnetic fields to make a band structure. This is a sketch of a simple band structure, and to hybridize the electromagnetic field with the electronic states to break some symmetries or dramatically alter the band structures in momentum space. When you have a time-dependent periodic field, which is intense enough, you can actually induce dramatic changes in the band structure, which translate into a mixing of Hamiltonian terms that gives you, in the steady state limit, gives rise to a different Hamiltonian with respect to your starting band. So the quantum state and the quantum-driven state will have different properties with respect to the one that we can elicit at equilibrium, that you can observe at equilibrium. Fluid engineering has been pioneered experimentally in the context of quantum materials, has been pioneered by the Getty group at MIT. So in 2014, they started working on topological insulators, and since then there has been more and more sophisticated experiments in this area where Fouquet states were seen as replicas, as coherent replicas of band structures. Then there's been a flurry of other experiments in graphene, TMDs, Van der Waals magnets, and certain oxides. But if you take a snapshot of the field as here, you can actually notice that there is a significant. And basically, when you look at all these experiments, all these experimental realizations of Fouquet engineering are involving reconstruction or driving of weakly interacting states, weakly interacting electron gases in certain conductors, or single ion states. So very simple underlying quantum states. And a big question is whether Fouquet engineering can be extended to states that are strongly interacting and where the wave functions are really many body wave functions with strong electronic interactions that cannot be described in some sort of neat field theory. So the question then is whether we can achieve Fouquet engineering of strongly correlated systems. And the reason why I'm particularly interested in this is that strongly correlated systems manifest among some of the most fascinating phenomena in the realm of condensed matter. And in particular, they give rise to very important fold-induced responses, very novel fold-induced responses. So there's been over the years significant work to study, as an example, phenomena like light-induced superconductivity, light-induced ferroelectricity, and ferromagnetism in strongly correlated materials. And by tailoring the properties of this system, you can think about generating new interesting quantum phases or functional phases. There has been significant theoretical work to propose Fouquet engineering for correlated systems, but experiments have been lagging behind, mostly limited by concerns about the presence of strong dissipation and interactions that may need to be progressed. So the question is, if you have a Fouquet engineering state in a strong correlated system, how can you certify it in some way? Okay, so here comes our work. So we decided to tackle this problem and to tackle it in a system that is quite prototypical. That is essentially a one-dimensional chain. So we decided to target the prototypical many-body state that is a Hubbard exciton. And it's a bound state of holes and double occupancies in a one-dimensional copper oxide, strong to copper 3. This material has been interesting in the field for many different reasons. It's a prototypical spin half knot insulator in one dimension with almost textbook spin charge and spin orbital separation. And it exhibits bound Hubbard exciton states. There has been a long work, quite a sizable amount of work on this material in the early 2000s by the Tukura group. And this is a good starting point to do experiments in a context that is quite controlled. And then can be modeled in a very accurate way. So now let me tell you about the optics of this material. So if you have Hubbard excitons in this material, you actually end up having, so you can calculate the energies, the energy levels of this, of the underlying Hamiltonian of this material. And you will have a ground state, and in general, excitons will take the form, will take two different combinations, will appear in two different combinations. We'll have a wave function that is odd with respect to the center of mass, and one that is even with respect to the center of mass. So you can have hopping events left or right, and of your to form on doublons, and this will appear in these two combinations that are nearly degenerate. when you look at the optical properties, one of these excitons is dark, one is bright. You have a very insulating state with an optical conductivity that peaks at about 1.7 eV. And what the Tokura group discovered early on was that the near degeneracy of these two excitonic states gives rise to a giant optical nonlinearity. So a very large third order optical response. And this is because there is a dipole matrix element that connects the two excitonic states that is really large because the wave functions overlap a lot. All right. This gives rise to very efficient third harmonic generation. Now, this is important because this means that the Hubbard excitons can be interrogated with third harmonic generation. And so we can actually use higher order responses to study the symmetry of these states and the symmetry of the quantum state as it becomes clear. Now, let me try to qualify what I said at the very beginning. So we want to do some kind of quantum control on this object. And what we can do in this context is to start by taking the two excitonic states. So you have two excitonic states that are nearly degenerate, and they actually define a Bloch sphere. So these are odd and even exciton states. And it turns out that when you use non-resonant periodic driving, when you do Foucault testing of these states, you have two main effects that can result from the perturbation, from the electromagnetic perturbation. One is a shift of the energy levels, and one is wave function mixing. This is essentially the same quantum mechanics that we teach our undergraduates. And nevertheless, when the two states are degenerate to first order, mixing is the dominant contribution, and you will end up having that the perturbation induced by the electromagnetic fields mixes the odd and even states, generating essentially a rotation on the Bloch sphere. So the mixing can be really conceptualized as a rotation on the Bloch sphere. Now, what we do in our experiment is that we take very tailored mid-infrared pulses, such as the one shown here. This is an experimental carrier envelope phase stable pulse generated in my lab. We have an oscillating electric field, and this oscillating electric field actually assumes different values as a function of the rotation. And if you initialize your exciton in the odd state, the ungerade state, you will have a certain third harmonic peak. As you start cranking up the field during the period of oscillation, you will have a precession of the Bloch vector on the Bloch sphere. And as you start mixing more and more, as you go more and more towards the dark state, the third harmonic will decrease. And you will end up in a situation in which if you have a complete inversion of the Bloch vector from the ungerade to the gerade state, you will have essentially zero third harmonic. If you cannot resolve the subcycle rotation, you will actually have cycle integrated reduction of the third harmonic generation. So the third harmonic can actually be used in principle as a way to measure really the rotation on the Bloch sphere. So for those of you who ask, okay, how is this related to the Foucault problem? So to the Rabi problem, when we usually study Rabi oscillations in the conventional quantum optical Rabi problem, we actually have a situation in which the separation of the states and the pump are larger than the coupling strength. In this system, since you have states that are nearly degenerate, we are actually in a slightly different regime. We are in a strong coupling quantum optical Rabi problem, in which essentially your Rabi oscillations become locked to the frequency of the pump. Okay, and this is a different regime with respect to early experiments that were done on semiconductor quantum wells and spins by, as an example, pioneers of fields like Ashwell, Shervin, Kami model. So the experimental platform at this point is clear. We have our mid-IR pump, we have a near-IR probe, and we studied the third harmonic output. So we get one photon in, we check for photons at 3 omega out, and we study this as a function of the pump probe delay with respect to the mid-IR field. And we drive our chains with pulses at about 0.12 eV that are really very close to this region of transparency. We are well into the gap of the system in the transparency window. So we are not really absorbing pump photons per se. And this is what we observe. So we observe that starting from this equilibrium curve, that is the one in purple, we end up in a transient state in which the third harmonic generation is reduced. And it signals the fact that the third harmonic response is suppressed as it should be if you are mixing the states. But nonetheless, if you start doing polarimetry on this state, you can actually rotate the polarization of the probe and the polarization of the pump. The polarization of the probe tells you that even in the suppressed state, you actually have that the states preserve the same symmetry. So you're not mixing other electronic states belonging to other chains and so on. And while the rotation of the middle ear pump follows exactly a Bessel function to the fourth, as you expect from a Floquet dressing of the state. So this is suggestive of Floquet. We measure the time dependence, and we actually see that this phenomenon occurs only at overlap between the pump and the probe. And based on the yield of the third harmonic at each stage, we can actually make an estimate of how much we are rotating this wave function. And we see that essentially as the field becomes larger and larger in your envelope, the wave function should rotate by a sizable angle. And so you will have a polar rotation in excess of pi half. This is an estimate based on a 3-level approximation. Can we do something better? We know that this is essentially something compatible with Floquet. We want to demonstrate it in a more systematic fashion. And so what we did was to actually look for sidebands. So if you have a periodic motion, you should actually see the appearance of sidebands in the harmonic response that are located at plus or minus the pump frequency. And this is a calculation of what you should see. So you should see actually a splitting, you should see replicas of your excitonic levels. And these replicas will give rise to what people in AMO call mono triplet. So you should have actually a triplet of hits, one corresponding to the original transition, one at plus or minus the pump frequency. When you start accounting for coupling to the continuum and all the many body effects that we expect in the system, you actually have something a bit broader. But the hallmark of this Floquet driving is that not only you have a reduction of the third harmonic at the main resonance, but you also have an increase of the third harmonic yield in the gap. Okay, so the measurement that we can do is to scan the third harmonic and to look for this enhancement. And this is what we actually see experimentally. So if you are really above the gap, you see that the third harmonic doesn't really change that much. If you are at resonance with the excitonic peak, we see a depletion. But when we move below, when we go in the gap of the Martin slider, we actually see an increase of the third harmonic yield. And once you integrate the spectra, you see all these all these curve that is actually compatible with a Floquet renormalization of the third harmonic response. And from this renormalization of the third harmonic response, we can actually use a more sophisticated all-on-double model to actually calibrate what's the angle of rotation. And this is corresponding to a rotation of about pi/4. There are also some other technicalities for the aficionados that are essentially ruling out things that are not really Floquet renormalization of the third harmonic response. So this cannot be a chi-4 response because this is a centrosymmetric system. It's not an excitonic shift because these peaks are too large with respect to possible shifts of the third harmonic spectrum. And we don't really have trade-offs with other nonlinearities. So we checked all of this. And once you start cranking up the field, you can actually build a table to calibrate how big of a rotation you have for each incoming field. So essentially, for fields of the order of 1.7 megavolt per centimeter, we can actually achieve a pi half rotation of the state, which is quite remarkable. And the complete rotation should occur at a complete pi rotation should occur at about 3 megavolt per centimeter. So the summary for this for these experiments is that we are demonstrating essentially a coherent rotation of a many-body wave function by about pi half. And this is something that got me really excited because in principle, once you achieve pi half, you can think about building more complex sequences and do really a quantum control of these states. And I just wanted to say that, so if you think about, so there has been recent work as an example by the Looking group where you can actually use, you can actually synthesize arbitrary quantum control sequences based on pi half pulses. And once you have pi half, you can actually build from the simplest, you can do Ram's interference, echo, and more complex sequences. But in principle, these are all ingredients that allow you to generate average flow Hamiltonians with pulse sequences. And this is something that, while it's done in the context of any sensing and so on, it's something that it's a concept that can be generalized also to quantum materials experiments, such as the one demonstrated here, by introducing pulse shaping techniques. And this is a bit the frontier for this field, because once you do pulse shaping to generate pulse sequences to control the excitons, you can think about doing more complex manipulations of these states. And as an example, use pulse sequences to synthesize for induced coherent phases. As an example, can I use this to induce an exciton condensate? Or perform high temperature quantum sensing, because these excitons live at very high energies. And all these experiments were done at room temperature. And you can think about doing manipulations that don't require very fine-tuned environments. And finally, there is interest in using these kind of controls for high temperature and high repetition rate logical operations. So this is a bit where I see this direction going. And in addition to demonstrating flow engineering of a correlated wave function, of a many-body wave function, these states can actually be functionalized for more practical applications in the future. And I think this is a very exciting area of development for ultra-fast experiments in the years to come. Before closing, I would like to acknowledge all the heroes of this story. So this work has been done almost in line with the experimentally by my former postdoc, Denisa Bagusheva, who's now a colleague of him at ISTA. And for the theory, we worked together with Martin Klassen and Deborah Carmichael. And we also work with Dante Kennes, with the Brookhaven National Lab, in particular Chris Soames and Igor Zarizniak, and with Angel Rubio and the PhD at Hubbard. And this work was supported by the US Department of Energy through an award which is right now in a Schrodinger cat state. It's undetermined. But yeah, with this I will close and thank you all for your attention.
So thanks for the nice talk. You know, when you have a many-body system and you want to blockade, you have this problem of blockade. You have a many-body manifold, and eventually you will absorb phonon and thermalize it in temperature, unless you have some mechanism like many-body localization could exist or others. So what is the why do you expect here that this blockade heating will not happen if you do it for longer than 5 or 2? If you do more complex pulse shaping, can you actually engineer an Hamiltonian without thermalizing at very high temperature because you start absorbing all this blockade photons effectively?
That's an excellent question. I think that the answer to this question is that what saves you. from runaway heating in these experiments is really the space, the relative space of dissipation timescales and driving timescales that we are applying. So these experiments are done at 1 kilohertz so far. We are experimenting with experiments going up to the megahertz, but the way the system dissipates, these materials tend to dissipate, especially when you have relaxation of let's say carriers, they're coupled to magnets and so on. They relax over 100 femtosecond timescales, or they tend to dissipate at very fast timescales. And I think the dissipation in these systems is really efficient.
So this will not kill the coherence of this will not kill the coherence of your Fourier evolution, or it helps
I can tell you experimentally it doesn't do it. And now we can have a conversation about how this is all possible, but I can tell you that we started asking ourselves, okay, what if this evolution was not coherent? If we had lots of decoherence, then you would not see the side. So you would the Fourier side would be completely smeared. You would not have enough coherence to build up Fourier side. And you would also see some other telltale signs of heating. As an example, like picosecond time steps that we don't see. This is all resolution. So I think the fact that the pump is low energy, the fact that you are at a low rotation rate, that somehow the time scale, the driving is also it's very low energy. This is not a Fourier experiment in short pumping with a frequency that is much larger than any characteristic energy stable physics, which is usually the usual Fourier approximation to build an effective anatomy. So I think all the linear combination of these things actually puts you in a state that is practically very active, which can build up coherence.
Thank you. Yeah, beautiful talk. Could we flash back to the slide where you show the sideband formation? Yeah, this one. So if I understand correctly, if this is due to Fourier, then we expect sidebands to be both on the left and right hand side of the mean V. So it looks like you're mainly focusing on demonstrating the one on the left. Do you have any comments about whether you have evidence for the one on the right?
Yes, this is an excellent question. So, I will tell you that you can actually see this is a theoretical calculation. It was a theoretical calculation that we did before doing the experiment. And you can actually see from the theoretical calculation that the evidence of the sideband is already faint, if not absent, on the blue side of the resonance. And the reason is that the excitons in these materials exist slightly below the unbound particle continuum. So you have an unbound or unbound continuum. That is essentially above the Mach gap. And so what happens is that the exciton lives all right in this coherent because it's below the Mach gap. But this sideband will actually start overlapping with the Mach gap. And so will be essentially more prone to couple to unbound particular excitations that will destroy its coherence. So this is our interpretation about why you can actually see a very nice triplet if you are accounting for just a 3-level approximation. So if you go to the initial calculation of the energy states that I showed, if you just retain the lowest 3 states, ground state, and the 2 excitonic states, you see a nice triplet. But once you start putting everything above the Mach gap, you start having this blue resonance will get completely suppressed.
If I may just a very quick follow-up question. Are you able to do a tuning experiment, like tuning your photon energy and see the sideband moving?
So let me think, because here we are already tuning the driver to see. So to do this experiment, we have been already systematically tuning the third harmonic driver. So each of these points is a different experiment. But one thing, so when you say you want to see, you want to
Yeah,
see
so for
different
example, it means the total energy and sideband should also change according to.
yes, so we didn't do it at lower energies. So the answer is that I don't have this data, but I can tell you that we didn't do it at lower energies just because I think when we started doing this, we didn't have enough fields. That, let's say, if we wanted to go, this is already pretty low. It's about 120 milliev. So if you want to go to 60 milliev, it becomes technically a bit more challenging.
Thank you.
Any else for questions? If not, let's thank Matteo again and all the.